Imagine spending like 2 full weeks meticulously writing deployment scripts for a 5-organization blockchain consortium.
Oh, that sounds like a nightmare already.
Okay, I mean, you've defined your certificate authorities, you've configured your ordering nodes, mapped out the channels, everything.
Yeah,
You hit execute, the containers start spinning up, and then you sit there watching the entire network violently tear itself apart in real time.
that's brutal.
And why? Because somewhere buried in like line 4000 of a YAML file, one single node had a port mapped as a string instead of an integer.
Yeah, or maybe two peers tried to initialize the Genesis block at the exact same time because a shell script just fired off out of sequence.
Exactly.
It's basically the DevOps equivalent of building a 90-story skyscraper,
Uh-huh.
walking up to the top floor, and then realizing the foundational concrete was poured over a sinkhole.
Wow, yeah, that is a perfect way to put it.
You don't just fix a typo at that point.
Huh?
You often have to tear down the entire environment, scrub your Docker volumes, and just start the deployment sequence entirely from scratch.
The iteration loop is just agonizing.
It really is.
And if you are an enterprise developer tasked with deploying Hyperledger Fabric, that agonizing loop is honestly just a regular Tuesday.
Unfortunately true.
So our mission today in this deep dive is to dissect a major bottleneck in enterprise blockchain technology. We are looking at how to orchestrate a Hyperledger Fabric network without losing your mind to that exact type of technical chaos.
Which is a very worthy mission.
I think so. We are grounding our entire discussion today in this incredible piece of academic research. It's a paper titled Towards a Model-Driven Approach for Hyperledger Fabric Network Orchestration.
Yeah, this comes from researchers Melson Tellez-Borges, Raphael Z. France, and Fabrice Rus France.
Right, at Unijuí University down in Brazil.
Exactly, and it was supported by funding from CAPES and CMPQ.
The Unijuí team recognized that the existing paradigm for deploying fabric networks, it relies heavily on imperative scripting.
Yeah, you are essentially commanding the system step by step, do this, then do this, then do that.
Which is so fragile.
It's incredibly fragile. So what they introduce in this paper is a complete paradigm shift toward a declarative metamodel blueprint.
A metamodel.
Right. They've built a tool called the Fabric Network Orchestrator, or FNO. And instead of blindly executing commands, FNO uses a domain-specific language to mathematically validate the architectural logic of your network.
Before a single Docker container is even instantiated.
Exactly. Before anything runs.
It parses your intent, checks the physics of the network you want to build, and it catches fatal errors before they escape the compiler.
Which is huge for developers.
But before we get into the heavy computer science of how FNO parses these domain-specific languages and abstract syntax trees, we really need to contextualize the architectural debt of Hyperledger Fabric itself.
Yeah, we have to look back.
Because if you're a systems architect, you know that Fabric's complexity isn't a bug, right? It is a direct consequence of how enterprise blockchain evolved.
Right. We have to trace the architectural lineage to understand why we ended up with such a rigid, orchestration-heavy framework in the first place.
Because the foundational cryptography wasn't designed for distributed finance or decentralized corporate applications.
Not at all. I mean, if we look at the origin in 1991 with Stuart Haber and W. Scott Stornetta, the architecture was simply about cryptographically linking blocks of data.
Just to timestamp digital documents, right?
Exactly. They were using Merkle trees and hash chains to solve a very specific problem, which was preventing the backdating of digital records.
So it was essentially a decentralized notary.
Yes. There was no concept of a global state machine or some complex consensus mechanism guarding against Sybil attacks.
Which means anyone trying to build a global financial system on that early tech would hit a wall.
Right. That specific leap required the introduction of Nakamoto consensus in 2008.
Ah, the famous Bitcoin white paper.
Exactly. Nakamoto didn't invent the blockchain data structure, but he or they introduced proof of work.
Oh.
And that was an economic mechanism to achieve decentralized consensus in a trustless peer-to-peer environment.
So Nakamoto solved the double spending problem without needing a central bank or an intermediary.
Right. But the limitation there is that the script language is intentionally Turing incomplete.
Meaning you can't run complex loops or full programs on it.
Right. It is designed solely for transferring a specific native asset.
Which brings us to the pivotal shift in 2014 with Vitalik Buterin and Ethereum.
The big leap.
Yeah, because Ethereum introduced the EVM, the Ethereum Virtual Machine, which turned the blockchain into a Turing-complete state machine.
Suddenly, we aren't just logging transactions. We are storing executable code-smart contracts, directly on the ledger.
The paradigm shifts from a decentralized ledger to a decentralized computer.
It does. But here's the architectural friction that ultimately necessitated Hyperledger Fabric.
Okay, let's get into it.
Ethereum, by default, is public, it's anonymous, and it's entirely permissionless.
Anyone can join.
Anyone. And every node in the network must process every single transaction to update the global state.
Which is a complete non-starter for enterprise environments.
Oh, absolutely.
I mean, if you are a consortium of European banks or a global healthcare supply chain, you cannot broadcast your smart contract logic and your state transitions to a public network.
No, you can't have anonymous nodes verifying your proprietary data.
You think about a public park, right? Anyone can enter, anyone can transact, anyone can sit on the bench and listen to your conversation.
That's a great analogy.
But an enterprise needs a high-security corporate building where you need an ID badge to access specific floors.
You absolutely do. The regulatory frameworks alone, like GDPR or HIPAA, they make public blockchains fundamentally incompatible with most enterprise use cases.
Because enterprises require privacy, they need known identities, and they need deterministic finality.
Right. Proof of work or even public proof-of-stake consensus models don't guarantee immediate finality. They offer probabilistic finality.
Which means a transaction could theoretically be rolled back.
Exactly. You might have chain reorganizations. In a high-frequency trading settlement system, you cannot have a transaction reversed just because a longer chain suddenly emerged.
So enter Hyperledger Fabric in 2018.
Yes. Originally incubated by IBM and later hosted by the Linux Foundation.
And Fabric basically throws out the public blockchain architecture entirely, right?
Completely. It is a permissioned blockchain. It abandons anonymous consensus in favor of pluggable, deterministic consensus mechanisms.
Like Raft or Byzantine fault tolerance?
Exactly.
Yeah.
And that permission nature completely rewrites the infrastructure requirements.
This is where the headache starts.
Oh, yeah. In Fabric, participation is strictly governed by cryptographic identities. You cannot interact with the network unless your identity has been issued by a recognized certificate authority within the consortium.
So there's no anonymous wallet addresses. You are known.
You are known, and your actions are tied to your corporate identity. Furthermore, Fabric introduces a unique execute order validate architecture.
Wait, how is that different from Ethereum?
Well, in public blockchains, transactions are ordered into blocks first and then executed by all nodes. Fabric flips this. Transactions are executed by specific endorsing peers, then they are ordered, and then they are validated.
Okay, so this allows for incredible scalability and privacy.
It does, because you can have isolated channels of communication where only the specific organizations involved in a transaction even see the data.
Or execute the chain code,
All right.
which is what Fabric calls smart contracts.
Right. But the trade-off for all this privacy, modularity, and pluggable consensus is just an absolute nightmare of orchestration.
Because you have so many moving parts.
Exactly. The strict identity requirements and the distributed nature of the endorsing nodes, the orderers, the certificate authorities, it creates a massive tangled web of dependencies.
Which is exactly the Hyperledger headache the Unisui researchers are targeting.
Right. If you want to develop a smart contract in Fabric, you can't just spin up a local environment with a single command.
Like you can with an Ethereum tool such as Ganache.
Right. Ganache is essentially a one-click local blockchain. It mocks the consensus layer so you can just test your Solidity code quickly.
So, question. Why can't we just have Ganache for Hyperledger Fabric? If IBM is backing this, why are we still using clunky manual shell scripts?
Because mocking a Fabric network fundamentally defeats the purpose of testing a Fabric network.
Oh, interesting. Why?
Because the complexity of Fabric is the network topology itself. A developer has to manually configure the certificate authorities to generate the X.509 certificates for every single admin, peer, and user.
That sounds tedious.
It is. And then they have to configure the ordering service, which requires its own Genesis block. Then configure the peers, join them to specific isolated channels, and install and instantiate the chain code on those specific peers.
And historically, developers have managed this web of dependencies using brittle shell scripts.
Mostly, yes. You're passing cryptographic material between Docker containers using volume mounts, relying on environment variables to point node A to node B.
It is deeply imperative. You are writing a script that says, wait 5 seconds for the CA to start, then use the Fabric CLI to request a certificate, then pass that certificate to this other container.
And the fragility of that imperative approach cannot be overstated. Shell scripts lack idempotency.
Meaning if they fail, you can't just run them again safely.
Exactly. If a script fails halfway through, The environment is in a corrupted, half-initialized state. You have jangling Docker networks, orphaned cryptographic material, and zombie processes running in the background.
Now, surely the enterprise community didn't just accept this. When looking at the source material, Table 1 in the paper details a very comprehensive analysis of previous attempts to solve this orchestration bottleneck.
Yes, the landscape is basically littered with partial solutions.
Let's talk about those.
Well, the official Fabric test network is the most prominent, but it fundamentally relies on massive bash scripts.
So it's still imperative.
Yes, and it requires the Fabric CLI binaries to be installed locally, which pollutes your host machine's environment. And worst of all, it lacks any intelligent pre-deployment validation. It executes blindly.
Okay, what about community tools? Because I know there are things like Fablo. Fablo attempts to abstract the bash scripts away, right, by introducing a declarative configuration written in YAML or JSON.
Yes, and Fablo is a massive improvement in terms of developer experience because of that declarative shift. You state what you want the network to look like, rather than writing the steps to build it.
That sounds like what this paper is doing.
It is similar, but the UniJUI researchers highlight a critical limitation. Fablo only performs syntactic and schema-level validation.
Okay, let's clearly define the boundary between syntactic validation and semantic validation, because this is the core differentiator of the new FNO tool we are diving into. Syntactic validation is basically just a grammar check, right?
Exactly. If you are using a JSON schema, syntactic validation ensures that your brackets match, your indentations are correct, and your data types align.
So if a field expects a string and you pass an integer, the schema validation catches it.
Right. But it has absolutely no understanding of the business logic or the architectural constraints of the domain.
Okay, so if I configure a YAML file for Fablo and I tell it to map a port to the word banana, the syntax checker might catch that because it expects a number.
Yes, it would catch banana.
But what if I map the port to -500? Or what if I declare a channel but don't assign any organizations to it? Syntactically, the YAML is perfectly valid, right? The schema is satisfied.
Precisely. A schema checker doesn't know that a Fabric channel requires at least one organization to function. It doesn't know that a network must have exactly one organization designated to bootstrap the Genesis block.
It's blind to the rules of the game.
Exactly. Tools like Fablo or web interface tools like FabNet, HFabD plus M, and SBC, they might hide the shell scripts behind a clean UI, but they are still fundamentally ignorant of Fabric's architectural rules.
So they will happily take your semantically broken configuration, generate the shell scripts, and try to deploy them.
And that drops you right back into the agonizing iteration loop we talked about.
You don't find out your architecture is flawed until the Docker containers are already crashing. You're debugging runtime errors instead of compile time errors.
And in software engineering, pushing error detection from runtime back to compile time is basically the holy grail of productivity.
Yeah.
You want the system to reject your flawed logic as early as possible.
Which brings us to the UniJUI University team. This is the exact gap they fill with their model-driven approach. They decided to stop building better shell scripts and instead build a metamodel.
Right. The metamodel brain.
Let's really dissect the DNA of this Fabric Network Orchestrator. What exactly are we talking about when we say metamodel in this context? How is it different from just a really strict JSON schema?
A metamodel goes beyond defining data structures.
Yeah.
It defines the semantic relationships, the constraints, and the operational rules of a specific domain.
And in this case, the domain is Hyperledger Fabric architecture.
Exactly. The researchers designed a domain-specific language, or DSL. When you write a configuration for FNO in YAML, TOML, or JSON, you aren't just filling out variables for a script.
You are writing code in a language specifically designed to articulate Fabric topologies.
Right, and the FNO engine acts as a compiler for this DSL. It parses your configuration file into an abstract syntax tree.
An AST, so it builds a mathematical graph of your intended network in memory.
Yes, and that graph is where the power lies. By loading the entire network topology into memory as interconnected objects, FNO can evaluate the state of the network holistically.
So it doesn't just read line by line, it actually analyzes the relationships between nodes.
Exactly.
Let's walk through the hierarchy of this metamodel, because the paper provides a really detailed UML-style diagram showing how these entities relate.
Yeah, it's a very clear structure.
At the absolute root of the tree, we have the config entity.
The config entity establishes the global boundaries. It defines the output directory, where the generated cryptographic artifacts and Docker Compose files will be written.
Right.
and it defines the network attribute, which dictates the namespace of the isolated Docker bridge network that will encapsulate all the containers.
Fairly straightforward, but nested immediately within that, we hit the capabilities entity. And this is where things get heavily tailored to Fabric-specific quirks.
Yeah, Fabric has a highly granular versioning system. Because it's a consortium network, you might have Organization A running cutting-edge node software, while Organization B is lagging behind on an older release.
Because enterprises move at different speeds.
Exactly. So to maintain consensus, Fabric enforces capabilities at 3 distinct levels: the channel layer, the orderer layer, and the application layer.
So the channel capability dictates what features the channel itself supports, regardless of the nodes connected to it.
Correct. The metamodel addresses this by centralizing the capability definitions at the network level. You declare your baseline boundaries, perhaps version 2.0 or 2.5 globally.
But hold on. If we are strictly defining node capabilities globally at the network level, aren't we just trading orchestration complexity for version locking rigidness?
What do you mean?
Well, what happens in a real enterprise consortium when a member absolutely refuses to update their pure binaries? If the metamodel forces a global version lock, it's basically useless for a real-world decentralized consortium.
That is an excellent pushback, and the researchers anticipated exactly that constraint.
Oh, they did?
Yes. While the capabilities entity centralizes the baseline, the metamodel is designed with overriding polymorphism.
Meaning?
Individual organization and node entities within the DSL can explicitly declare their own specific binary versions overriding the global baseline.
Ah, so the local node definition inherits from the global capability but can override it if necessary.
Exactly. And because F&O builds that abstract syntax tree in memory, it can mathematically verify if the specific local override is actually compatible with the global capability baseline.
So if Organization B tries to run a 1.4 peer on a channel that requires 2.0 application capabilities, F&O flags the version matrix mismatch instantly.
Instantly, before anything runs.
That is a massive time saver. We'll dig into that version validation more in a moment. But moving down the metamodel hierarchy, we have profile and channel.
Profiles are essentially abstract templates. In Fabric, you often have multiple channels that share identical access control policies and consensus configurations.
Right.
Instead of repeating that configuration for every single channel, the metamodel allows you to define a profile once. Then you instantiate multiple channel entities that simply inherit from that profile.
So it brings object-oriented principles like inheritance and DRY, don't repeat yourself to infrastructure as code.
Exactly. It makes the code much cleaner. Then we drill down into the actual governance layer.
Right.
The organization entity.
The organization is the administrative heart of the permission network.
Yes, every organization must have a defined name and a unique domain. The metamodel also exposes a user's attribute.
What does that do?
It's an integer that dictates exactly how many client identity certificates the certificate authority should mint for this specific organization during the generation phase.
So if you don't declare it, F&O defaults to generating a single administrative identity.
Right. But there is a crucial Boolean flag inside the organization entity, a switch called bootstrap.
Let's talk about bootstrap, because this touches on one of the most fragile aspects of Fabric orchestration, the Genesis block.
It's notoriously tricky. When a network boots up, the ordering service needs a foundational block 0 to establish the initial state and the consortium policies.
And multiple organizations cannot simultaneously attempt to create the Genesis block, right?
No, it creates an immediate fork and a massive race condition.
So a standard shell script would just fire off commands to every org simultaneously, and whoever hits the orderer first wins while the other processes crash and burn.
Precisely. The metamodel fixes this by requiring you to explicitly declare one and only one organization with the bootstrap flag set to true.
And nested inside those organizations, we finally hit the physical infrastructure, the nodes.
Yes. Every organization requires a certificate authority. And because F&O utilizes containerized execution, meaning it manages all the Fabric binaries inside Docker containers so you don't pollute your host machine, you have to define an expose port attribute.
Which bridges the isolated Docker network namespace back to the host machine's interface, allowing you to actually interact with the CA from outside the container.
You also define your orderer nodes and your peer nodes, mapping their ports and domains. But the peers have an additional, highly specific Boolean flag. is anchor.
This relates to the gossip protocol, right? In a multi-org network, peers from different organizations need a way to securely discover each other, to sync ledger data.
Yes, Fabric relies on an epidemic gossip data dissemination protocol. Nodes randomly share ledger data with other nodes to ensure eventual consistency across the network.
But you don't want every single node randomly pinging external organizations. That would be a nightmare for firewall rules.
Well, IT security would shut that down immediately.
So you want a designated ambassador.
Exactly. The S-anchor Boolean designates a specific peer as the anchor peer for its organization. It acts as the primary ingress point for cross-organization gossip.
So let's zoom out. We have this incredibly detailed, object-oriented representation of our blockchain network. We have written our YAML file using this domain-specific language.
Right.
Now we hit the core innovation of the paper, the 4 pillars of validation.
This is where FNO moves from being just a neat configuration wrapper to a mathematically rigorous orchestrator.
FNO is a cross-platform command line interface, and the operational workflow consists of 4 phases: specification, validation, artifact generation, and network deployment.
The validation phase is what stands between our configuration file and the artifact generation.
Artifact generation is where FNO actually writes the underlying Docker Compose files and uses the Fabric binaries to mint the certificates.
Right, but it refuses to generate a single artifact until the AST, the abstract syntax tree, passes 4 distinct pillars of validation.
Let's dissect these pillars, because this is where the semantic versus syntactic difference truly shines. The first pillar is structural validation.
Structural validation ensures referential integrity across the graph. When FNO parses the YAML into memory, it traverses the tree to guarantee that every identifier is unique.
So it checks that organization names do not collide.
Yes. It ensures domains and subdomains are completely unique across the entire network topology.
It also verifies pointers, right?
Right.
If a channel declares that it is inheriting from a profile named high security template, structural validation traverses the tree to ensure that high security template actually exists in the profile definitions.
Exactly. If it doesn't, the compiler throws a referential integrity error immediately.
But structural integrity is just the skeleton. The organ system, the actual business logic of the network, requires semantic validation. This is the second pillar.
Right.
How does the engine actually perform semantic validation? It's one thing to check if a string matches another string, but how does the code mathematically prove a Fabric constraint?
It uses invariant checking against the in-memory graph model.
Invariant checking.
Yeah. The UniGUI researchers programmed specific Fabric architectural rules into the FNO validation engine as strict invariants. For example, the engine runs a function across the entire network state, looking at the bootstrap Boolean we discussed earlier.
Okay.
The invariant rule states, the sum of all organizations where bootstrap equals true must equal exactly 1.
So if the sum is 0, the network lacks a Genesis block initiator and cannot start.
Right, and if the sum is greater than 1, the engine flags a race condition.
That is so elegant.
It performs similar invariant checks for the anchor peers. The rule dictates that an organization should have at most 1 peer with isAnchor set to true.
Right.
Furthermore, it checks the relationships between channels and organizations. A channel must reference a profile, and that profile must include at least 1 organization. You cannot instantiate a channel with 0 participants.
It is basically running a physics simulation of the Fabric architecture. If the physics are impossible, it halts.
That's a great way to look at it.
The third pillar is versioning validation. We touched on this, but how deep does the dependency matrix go?
It goes incredibly deep. FNO is designed to target modern Fabric deployments, so the engine's first check is to ensure that the global capability baseline is set to at least version 2.0.
So if you try to declare a 1.4 baseline, it rejects the model.
Yes, but more importantly, it performs cross-component compatibility checks.
Right. Checking the local node overrides against the global capability.
Exactly. It traverses the node entities, extracts the explicitly declared binary versions, and cross-references them against a hard-coded compatibility matrix.
Wow.
It knows that a peer running version 2.2 cannot participate in a channel requiring version 2.5 application capabilities. The engine computes these dependencies instantly, preventing a deployment that would inevitably fail at runtime during channel joining.
That saves so much debugging time. And finally, the fourth pillar, deployment validation. Now, at first glance, checking port numbers seems trivial compared to computing dependency matrices. Why dedicate an entire validation pillar to it?
Because in containerized orchestration, port binding physics are the source of most silent, catastrophic failures.
Oh, definitely.
FNO validates that every single expose port declared across every CA, order and peer, is a valid numeric integer strictly greater than 0 and within the bounds of standard TCP port ranges.
And crucially, it checks for collisions across the host machine mapping.
Exactly. You might have two completely different organizations, but if they both attempt to map their anchor peer to port 7051 on the host machine,
The Docker daemon will crash during deployment.
yes, FNO maps the entire port space in memory and flags the collision before generating the Docker Compose manifests.
The aggregate effect of these four pillars is profound. The researcher's tool transforms an unpredictable, highly volatile deployment process into a mathematically verified certainty.
It does. By the time FNR moves to the third phase artifact generation, you have near absolute confidence that the resulting cryptographic materials and container configurations will execute perfectly.
That is a massive claim to make in software engineering. You can't just publish an academic paper with a bold claim and say, trust our math. You have to provide empirical evidence.
And they did. The UWE researchers dedicate a significant portion of their paper to an experimental evaluation.
Right. They engineered 8 specific case studies, labeled C1 through C8, to stress test the validation engine and the deployment pipeline.
They fed these configurations into the FNO CLI, running the generate and deploy commands, and logged the outcomes.
Let's analyze the topologies they tested, starting with the successful deployments. Scenario C1 was the baseline test.
C1 was the simplest possible configuration to achieve a functional fabric network: 2 organizations, 1 orderler, and a single shared channel.
And how did FNO handle it?
FNO parsed the minimal YAML, validated the default parameters, generated the artifacts, and deployed the containers flawlessly. 0 manual intervention.
But enterprise networks rarely stay at 2 organizations. Scenario C2 scaled the topology drastically.
Yes. C2 introduced a 5-organization consortium. Furthermore, each organization was assigned 2 peers.
So that is 10 peer nodes, 5 certificate authorities, the ordering service, and the complex routing required to join them all to the same channels.
Manually managing the X.509 certificate generation for a 5-org network using cryptogen and config.exgen shell scripts is incredibly prone to human error.
Oh, I can't even imagine.
But FNO handled the scaling purely through declarative state.
You just change the number of orgs in the YAML, and FNO figures out the hundreds of cryptographic generation steps required behind the scenes.
Exactly.
Scenario C3 moved away from node scaling and tested architectural flexibility, specifically multi-channel networks with shared profiles.
It verified that the object-oriented inheritance model we discussed actually works in practice.
And C4 was perhaps the most crucial for enterprise lifecycle management. It tested cross-version compatibility.
They deliberately configured a network where different nodes ran on different minor versions of Hyperledger Fabric, testing the capability overriding feature. FNO validated the version matrix, generated the specific binary polls for the Docker containers, and the network achieved consensus successfully.
All 4 of those scenarios are brilliant proofs of concept. But honestly, as someone who has spent hours staring at Docker logs, I don't care how well a tool works when I write the code perfectly.
Right. You want to know what it does when you make a mistake.
Exactly. I want to know what the tool does when I write garbage code.
The true test of a compiler or an orchestrator is its philosophy of failing gracefully. And that brings us to scenarios C5 through C8.
These were intentionally invalid configurations injected into FNO to test the 4 pillars of validation. Let's start with C5.
Scenario C5 tested the structural validation. They wrote a configuration where a channel definition referenced an organization named org3, but they deliberately left org3 out of the network's organization definitions.
So what would happen in a traditional setup?
In a traditional shell script pipeline, the script might generate the certificates for org1 and org2, create the genesis block, and then suddenly throw an obscure null pointer exception when it tries to join the non-existent org3 to the channel.
And you were left with a half-built, corrupted network.
Right. But FNO caught it during the parsing phase. The engine halted immediately and returned the error. Organization not defined, org3.
It points you directly to the missing node in the tree. That's beautiful.
Scenario C6 targeted the versioning validation. They explicitly configured a peer node to run version 1.4, while the network capabilities required a minimum of 2.0.
And the validation engine halted the artifact generation and output. Pure version 1.4 is lower than required 2.0 point.
There is zero ambiguity. You aren't digging through Fabric peer logs trying to decipher why a gRPC connection was rejected. The compiler tells you your architecture is illegal.
Okay, what about scenario C7?
C7 evaluated structural uniqueness.
Mhm.
They duplicated an organization name, defining org1 twice in the configuration.
A very common copy-paste error.
Exactly.
Yeah.
And the engine immediately caught the referential collision and halted with the duplicate organization name, org1.
And finally, C8 tested the semantic validation layer. They attempted to declare a channel profile without assigning any participating organizations to it.
The invariant check we discussed earlier immediately failed. The engine reported, default profile must include at least one organization.
If you are an infrastructure engineer listening to this, those error messages are a revelation.
They really are. They transform the debugging process from a blind forensic investigation of scattered log files into a deterministic actionable checklist.
The orchestrator is acting as an architectural linter.
It entirely bridges the gap between formal specification and network deployment. By abstracting the imperative shell commands into a declarative metamodel, FNO forces the developer to focus on the business logic of the consortium, rather than fighting the plumbing of distributed container networks.
And looking at the conclusion of the paper, the Unijui University team has a very clear roadmap for pushing this paradigm even further. The current FNO tool targets Docker Compose, which is standard for local development and testing. But the future of enterprise infrastructure isn't Docker Compose, it's Kubernetes.
Exactly. And the researchers state that expanding FNO to natively support Kubernetes deployments is a primary future objective.
Which makes sense. In a Kubernetes environment, you are dealing with distributed pods, complex ingress controllers, persistent volume claims, stateful sets. The orchestration complexity is magnified exponentially.
But because FNO already models the network as an abstract syntax tree, writing a Kubernetes backend is just a matter of adding a new generator module.
So instead of translating the AST into Docker Compose YAML, the generator would translate the AST into Kubernetes Custom Resource Definitions, or CRDs.
You could even build a Kubernetes operator that watches the FNO configuration and continuously reconciles the cluster state.
They also plan to integrate the FNO command line interface directly into development environments like Visual Studio Code, likely utilizing the Language Server Protocol, or LSP.
That would be incredible.
Right. You wouldn't even need to run a command. As you are typing your YAML specification in your editor, the LSP would be running the FNO semantic validation engine in the background, highlighting referential integrity errors and version mismatches with red squiggly lines in real time.
Just like a spell checker for blockchain architecture.
And perhaps the most academically rigorous future work they propose is mapping object constraint language, or OCL, rules into the validation engine.
OCL is a declarative language specifically designed to describe rules that apply to unified modeling language models.
By integrating OCL, they would be pushing the orchestration process out of standard software engineering and into the realm of formal methods. You are mathematically proving the correctness of your blockchain architecture using the same rigor applied to aerospace control systems or nuclear reactor software.
It guarantees that the network topology is logically sound before a single byte of execution material is generated.
We have covered a massive amount of computer science and infrastructure theory today. We started by exploring how the need for privacy and strict governance pushed enterprise blockchain away from the public, permissionless models of Bitcoin and Ethereum,
leading to the highly modular, identity-driven architecture of Hyperledger Fabric.
We examined the severe technical debt created by that architecture, the fragility of imperative shell scripts, the lack of idempotency, and the inadequacy of syntactic schema checkers.
And we dissected the solution, a model-driven approach.
We looked at how a domain-specific language can build an in-memory graph of a network, allowing a semantic validation engine to enforce structural integrity, compute version dependencies, and prevent runtime port collisions before artifact generation even begins.
The Unijui team's Fabric Network Orchestrator represents a massive leap forward in developer experience.
It really does. But I want to leave you with a broader, somewhat philosophical thought that builds on this entire concept of metamodeling and strict automated governance.
Okay, let's hear it.
We just spent this entire deep dive discussing how we can successfully use abstract syntax trees and invariant logic to perfectly model, validate, and deploy the incredibly strict, multi-layered governance of a permissioned digital consortium.
Right.
We can mathematically define the roles, the organizations, the communication channels, and the exact rules of engagement.
Down to the specific node version.
Exactly.
Yeah.
So if we can encode that level of complex governance into a deterministic compiler for a digital network, what does that imply for the future of physical organizations?
That's an interesting question.
Could we eventually use these exact same types of metamodels to automatically structure, validate, and virtually deploy the legal, financial, and hierarchical rules of a real-world corporation? Imagine writing a declarative YAML file that defines a corporate merger. The semantic validation engine checks for regulatory compliance, antitrust invariance, and financial dependencies in milliseconds, highlighting legal collisions before a single contract is even drafted.
A spell checker for corporate law.
Yes. If we can formally model the DNA of a secure, multi-organization distributed network, how close are we to formally modeling the DNA of human enterprise itself?
That is something to think about.
Next time you are staring at a completely broken deployment pipeline or a tangled mess of corporate bureaucracy, just remember, the chaos usually exists because no one bothered to mathematically define the state of the world first. There might be a metamodel out there waiting to make sense of the noise. You just have to be willing to declare the blueprint.